Thank you very much for the invitation, and I'm very honored to, and I'm glad to give a talk in this big and a very daunting collection of audience. And today I'd like to talk about RAAGs in Diffeos. And it is joint work with Thomas Bldg, who is at Yale. So let's see. So Brian already defined what a quasi-isometry is. So I'd like to introduce a slightly stronger condition. So let's see. Let us first start with definitions. So let's say, suppose you have two groups, say GDG and HDH, and they are groups with metrics. Okay, so they are not necessarily discrete groups. There might be continuous groups. Anyway, so they have metrics. You can talk about a quasi-isometry and a quasi-isometric group embedding is the notion that I'd like to talk about today from G to H is a group homomorphism, injective group homomorphism. Which is a quasi-isometry. Okay. So quasi-isometry embedding, quasi-isometric embedding. So in other words, as Brian defined it, so a quasi-isometric group embedding is a map which coarsely preserves the metric. But as you have seen, it is not, so quasi-isometric embedding, this notion itself does not guarantee the injectivity or preserving the group structure. But this quasi-isometric group embedding requires that the group structure is also preserved. In other words, it is an injective group homomorphism. And yes?
Is there any relation between the group structure and the metric?
Not yet, not yet. So, but mostly we're going to talk about at least right invariant, mostly by invariant metrics, but not yet. Okay. So the main object of study that I'd like to talk about today is a right-angled arcing group. So I was kind of expecting that Karen would have defined it, but I guess it's my job to define it. She's going to use it tomorrow. So right-angled arcing group. So let's say gamma is a finite graph. Then one can define so-called right-angled arcing group. Nowadays, it is very often abbreviated as RAAG, but right-angled arcing group is the full word for it. On gamma is a group presentation. I'm going to use G gamma, and that will be a group presentation where the vertices are the generators. So I'll just say all the vertices in the vertex set will generate the group. And for each edge, there's a corresponding commuting relations. But today, I'm going to use the opposite of a usual convention. So in other words, that is two vertices are declared to be commuting if they are non-edge in the edge set. Okay. So I guess Karen will be defining it again in the opposite convention tomorrow. So for example, if you have just one vertex, then it is one generator, no relations, so it will be Z3. If you have a triangle, it will be 3 generators and no relations at all because there are no non-edges. So it is, this 3? What am I saying? This 3. So I'm going too fast. So F3, yeah, F3. So no edges. So no commuting relations. And as I said, so this is a big audience with daunting collection of experts. So it makes me nervous. If you have 2 edges, okay, what would it be? So this connected component corresponds to commuting relations, so direct product. And this edge corresponds to F2. So this will be F2 cross F2. Okay? And you can go on. And an interesting thing, so it's really far from the median, I realized. It should be somewhere here. Okay, so, right. And there is a recent, almost explosive development in geometric group theory and low-dimensional topology, and that is quite a lot of it is due to the richness of subgroups of right-angled arcing groups, quasi-isometrically embedded subgroups of right-angled arcing groups. So the first question one can ask is, what are which groups admit quasi-isometric group embedding into RAAGs? Okay. And there are lots of deep and very interesting results regarding this question. And because of the nice properties of right-angled arcing groups and this metric condition and group theoretic condition, it transfers to the properties of subgroups of RAAGs. So for example, the following are known. Probably one of the so actually what is true is lots of hyperbolic groups and hyperbolic manifold groups embed into right-angled arcing groups. So one of the earliest observation due to drums, which was much more refined by Crisp Vist in 04, is that the fundamental group of every closed hyperbolic, not necessarily orientable surface S with Euler characteristic less than -1 embeds into some RAAG. Maybe I should say each, because the choice of writing the arcing group, well, every is fine, sorry. Yeah. So the fundamental group of hyperbolic surfaces, as long as it is not Euler characteristic -1 surface, embeds into some right-angled arcing group. So it is quite an early result compared to the other more surprising results. And then, a recent hype about recent big development in low-dimensional topology in publication date. So every closed hyperbolic 3-manifold group virtually. So here, actually not just embeds, but it admits a QI group embedding. So it is not only a group theoretic embedding, but also it coarsely preserves the metric. Also, virtually QI embeds, so it is quasi-isometric and group embeds into RAAGs. Okay. Let's see. Okay, and right. And regarding hyperbolic manifold, actually, so there's Piotr-Przititsky and Danny Wise also proved that mixed manifold groups and graph manifold groups with boundary virtually embeds into Ryding-Darting groups. But regarding hyperbolic manifold groups, there is a result by Bergeron, Wise. This is published in 11. That for every D, there exists a closed hyperbolic D manifold group. That admits a QI group embedding into some RAAGs. So in every dimension, there is an example of closed hyperbolic D-manifold groups, non-trivial closed hyperbolic D-manifold groups into Ryding-Darting group. But these theorems don't really have a good control over the target. So for example, you don't have really control of the homological dimension of the Ryding-Darting group, or the abelian rank, in other words, abelian rank of the target group, or the shape of the target group. So the question that I'd like to address today is more focused on the target. In other words, so given Ryding-Darting group, so which groups admit a QI group embedding into G gamma, okay? Or, so this turns out to be quite a complicated question. So you want to know the subgroup structure of a given Ryding-Darting group. Well, for free groups, any subgroup is free. For abelian groups, free abelian groups, just every subgroup is abelian. But for general Ryding-Darting group, the subgroup structure, knowing the subgroup structure, answering certain questions regarding subgroups is quite a complicated question. And there are some algorithmic obstruction that we're going to see today soon. So, but you can restrict the class of subgroups and still ask the same question, and still the complete answer is not known. So which RAAGs admit QI group embedding to G gamma? So you can restrict to the class of Ryding-Darting groups, and which of those can embed into Ryding-Darting group. Okay. So this is one of the questions that I'd like to talk about today. And referring to the title of the talk today, one can also talk about diffeomorphism groups of manifolds. So it is rather a propaganda, rather a result. So there is something called universal property of Ryding-Darting groups. And that is a propaganda of explaining why Ryding-Darting groups are so ubiquitous as subgroups of many diffeomorphism groups or mapping class groups. Namely, if you have say, elements, distinct elements in diffeomorphism group of a manifold, say smooth diffeomorphism group of a manifold with smooth structure, the dimension doesn't matter, then you can talk about the intersection graph of supports. Support of psi n. Okay. So in other words, so there will be n vertices, okay, and you join two vertices if the corresponding supports are intersecting. So edge means intersection. And if two supports are disjoint, you do not join those two vertices. Then there is a a natural group homomorphism from G gamma to diffeomorphism group of M, right? By sending, say, ith vertex to psi I. Or we can actually raise psi I to the arbitrary power. You still have group homomorphism. The reason is if two support, so support means the collection of the closure of the set of non-fixed points by that diffeomorphism. And if two supports are disjoint, then obviously those two diffeomorphisms will commute. Okay? So here, non-edge corresponds to intersection in the target. Yep. So if two vertices are not joined, they commute, and they will be the corresponding diffeomorphisms will commute. So, right. So this is a motivation of. So usually the diffeomorphism groups of manifolds are quite complicated objects, and many of the diffeomorphisms that I'm going to talk about today are not fully understood. And writing the quasi-asymptotically embedded right-angle groups there, we find some geometric information about the diffeomorphism groups. So, or proving certain embeddings are never possible. So, namely, the third question would be, so which groups, which RAAGs arise as admit QI group embeddings into diff of M, where M is a smooth manifold, just your favorite one. All right, so I'm going to talk about that too. Yeah, sorry. So, right, group embedding and certain subgroup of into with metrics defined later. Yeah. So as I said, this blackboard is a propaganda. Okay. Okay. Thanks. So let's see. Oh, so what is the question? Oh yeah, you're right. So yeah, I can make the question completely tautologically trivial, but yeah. So with metric which contain information about the diffeomorphism group, yeah, some good metric. Thanks. So let's see. Right. So let us start with question 2. So RAAGs in RAAGs and also in mods. Okay, so right, so let's see. First of all, notation is that if x and y are graphs, then there's a notion of induced subgraph. We write x less or equal to y if x is a subgraph and x is maximal determined by its vertex set. In other words, it contains all the edges from y as long as it joins two vertices of x, a pair of vertices in x. So one immediate observation, not completely trivial, but easy observation is if x is in this subgraph of y, which is finite graph, then gx embeds into gy. And it is also quasi-isometric group embedding. It's almost trivially defined, so you just send each generator to its image in the target. And a refinement of the result is the following. So the theorem. So one direction is a joint work published last year, and so this will be this direction, and the opposite is a previous result of Bldg. Is that so? Let's say gamma is a finite graph, then say such that I'm just for simplicity consider rank 2 case only. So finite graph such that Z3 doesn't embed writing Darting group. Okay, let us consider rank 2 case. It is still complicated enough. Then there exists quite complicated, locally infinite combinatorially defined. So it is defined as the infinite union of certain combinatorial process. Combinatorially defined graph. I'll just call gamma extension, such that for any finite graph, so this graph completely explains all the Ryding-Dartin subgroups of G gamma, such that G lambda embeds into G gamma if and only if lambda is can be found as the finite induced subgraph of. Because of my conventional heresy today, I'll have to take the opposite graph. So this is the opposite graph. Yeah, let's see. No, I'll just stick to the, sorry. Yeah. I'll just stick to the opposite convention. Anyway, so the message is that if you have a finite graph and if the rank is 2 or low, so Z3 is not contained in G gamma, then you can combinatorially define certain complicated enough, locally infinite graph, so-called gamma E, such that it explains all the possible Ryding-Dartin subgroups in G gamma. And in this case, there exists a quasi-isometric group embedding, always. Okay. So in rank 2 or lower case, we are pretty much happy because we have a certain combinatorial object which explains all the Ryding-Dartin subgroups of G gamma. But because of this is an infinite union, it doesn't algorithmically answer the question of which Ryding-Dartin group is embedded into a given Ryding-Dartin group. Namely, so the open question is, so is it decidable that Gx embeds into Gy? So given x and y, yes?
Is there, supposing you only want to embed these jumping finite
So what is the question? Well, if there's an embedding from one to the other, if there's a virtual embedding between two Ryding-Dartin groups, and there will be an embedding between two Ryding-Dartin groups. Yeah, same question. Yes, yeah. So it is quite different from embedding some other group into writing it down. That's a completely different question. But for writing other groups, yeah, it's the same. Yeah. Any embedding, yeah. Yeah, it's different question. Yes, yeah. Yeah. Let's see. And I included mods in the title. So actually what we found is that extension graph is quite similar or plays a role similar to that of a curve complex. In other words, so yeah. Actually, yeah. Yeah. Yeah, I realize I got nervous. So the attribution was wrong. The attribution is supposed to be the next theorem. So it is a joint work, and this was supposed to be the combination of two works. So this is one direction, this will be the other direction. Is that, so now you can try to explain subgroups of mapping class groups, so which was defined in timely manner by Brian in the previous talk. So you can try to ask which writing Darting group can arise as subgroups of a given mapping class group. So abelian rank is certainly an obstruction, but is that it? Are there any other obstructions? So the answer is that, so in the rank 2 case, if rank is at most, so in other words, if the complexity, again, defined in timely manner by Brian in the previous talk, then one can explain all the writing Darting subgroups of a mapping class group by looking at this curve complex. So G gamma embeds into group theoretically, embed into mapping class group if and only if, let's use lambda, if and only if lambda appears in the curve complex and the opposite graph. Sorry. So this up means opposite graph or complement graph, which is often used in graph theory. So this is basically the vertex set is the same. You join an edge if there was not an edge in the previous graph, and vice versa. So this confusion about opposite is all due to the my heresy of using the opposite convention of the writing Darting group. If you use the opposite convention, this statement would be simpler. So if, in other words, if you find a finite graph, a curve complex, then there's a corresponding writing Darting group. But for low complexity, the opposite is also true. In other words, whenever you have a writing Darting embedding into a mapping class group, actually there are finitely many surfaces of complexity at most 2. Anyway, in that case, you can find that graph in the curve complex as an induced subgraph in the opposite graph. So let me make some remarks. So first of all, for rank larger than 2, in other words, in writing Darting groups which contain Z3 or mapping class group whose complexity is at least 3, those theorems are not true as is. So for RAAGs, this finding is due to Andrew Duncan, Montserrat Casals Ruiz, this is dash, this is hyphen, and Ilya Kazatskov. 13, and for maths, also for high complexity, it is not true as is. So this is, again, joint work, but there is a version for rank larger than 2. So one will have to consider a multi-curve complex rather than curve complex in that case. And the result is slightly weaker, And as I briefly mentioned, so abelian rank is not the only obstruction. For writing darting groups to be embedded into mapping class groups. In other words, there are infinitely many surfaces, infinitely many gammas, such that abelian rank of G gamma is only 2. But still, there are no embeddings from G gamma into mapping class group. And yeah. And also, this extension graph has nice metric properties. So it's a quasi-tree. In other words, it's quasi-isometric to simplicial tree, and there's an action by conjugation, certain action from writing darting group into quasi-tree. And this is a cylindrical action. It is a term due to Bldg. Due to Brian. And this acylindrical action on a hyperbolic space gives a canonical, so not involving any choices, canonical classification, elliptic or loxodromic of writing darting group elements. So this kind of all these definitions, this extension graph, do not involve any choices. So this gives a certain canonical classification of elements in writing darting groups. And for the remaining 25 minutes, actually I wanted to focus more on diffeomorphism groups of containing writing darting groups. So for the breach is the following observation. So actually the main observation that I'd like to present today is that every writing darting group admit quasi-isometric group embedding into some rack on a tree. Actually, yeah, I should be careful in writing it. So each writing darting group admits a quasi-isometric group embedding into some writing darting group defined by a tree. So of course, this tree depends on the choice of the writing darting group that you start with. And more precisely, I can give a recipe to find such a tree, roughly. So the construction of the tree is actually a somewhat natural approach. An approach which was a similar approach was also taken by Misha Kapovich in his paper on writing darting groups in symplectomorphism groups. So namely, the recipe is as follows. So let's say gamma is a connected graph, just arbitrary connected graph. If it is not connected, you can always add more edges so that it is connected. So just with a loss of generality, suppose you are given it a connected graph, then you can consider its universal cover. You can consider its universal cover. So it is a infinite tree, usually. And consider an induced subgraph, which is finite subtree. Consider an arbitrary finite subtree. Then there is a natural group homomorphism from writing the Artin group in gamma into writing the Artin group in T. In other words, so define, again, as soon as you choose T, this homomorphism is determined. Simply by defining V maps to multiplication of all of its preimages in T. In arbitrary tree. No, arbitrary order, you're right. So, yeah, good point. So, the thing is, the order does not matter because we are using the opposite convention. So, preimage is always a discrete set. That means they are commuting. Right? So, preimage, you're right. So, preimage is a discrete set. So, they all commute. So, the order of multiplication does not matter. And T is a finite tree by hypothesis, so it is finite product. No, yeah, right, yeah. So, stable set, yeah, stable set. Independent set, in other words, right? Of course, it might be empty if T is small, but just make it T very large, or just declare multiplication of empty set is trivial. Doesn't really matter, okay? So then the recipe is if T is large enough, the diameter of T is large enough, then T gamma T is an injective, is a QI group embedding. Okay. The proof of this is a cancellation argument, so I cannot go into the detail, but basically this is the recipe. Just find a fixed arbitrary base point in the universal cover, and let's say T is a R ball around it. If R is large enough, then this will be group embedding. Moreover, this will preserve the group structure coarsely. So, the first use of this is finding writing the Artin groups in braid groups. Let's say okay, so we'll consider pure braid group. It is a finite index subgroup of braid group. You can consider this as the configuration space, fundamental group of configuration spaces for I different from J, or often we'll identify this with a disk pure mapping class group with n punctures, fixing the boundary point-wise. Okay. And then, so this is a series of groups indexed by the number of strands, n. And this linearly indexed set contains actually all the writing Artin groups. And it can be seen in two ways. First of all, it can be seen as a a very trivial consequence of a theorem due to crisp Wist in proven in 07 that every G riding Darting group on a planar graph admits a QI, let's see, group embedding into some purebred group. Okay, therefore, it is a trivial consequence that every riding Darting group embeds into some purebred group by quasi-isometric group embedding. Okay, because of the main theorem, theorem A. So because every riding Darting group embeds into some riding Darting group defined by a tree, and then use Crisp-Wist theorem to embed riding Darting group on that tree into some purebred group, and it even preserves, coarsely preserves the metric. And so actually one can give a proof which is independent of, well, independent of Crisp-Wist paper in 07, although it is largely influenced. So how should I say, self-contained or independent proof would go as follows. So we have only to consider the case gamma is a tree. So let's say gamma is a tree. Let's say tree looks something like this. Okay. And say the vertices, there will be vertices. Then you can consider collection of small disks. Say dA, dB, dC, d of small d. In other words, consider, say, d of v, where v is the vertex set. Disks in D, whose intersection graph is gamma. Is gamma. Okay, you can do that because tree is planar. You cannot do that if the graph is a planar graph. I mean, sometimes it is possible, but you cannot always do that if gamma is not guaranteed to be planar. Okay. And let's say P. Consider a certain finite set, finite punctures large enough such that there exists a pseudo-analysis of, say, psi v supported on dv minus punctures. So it is a map which is identity outside dv, and on dv it acts as a pseudo-analysis of map as a puncture disk. And you can do that by taking out sufficiently many punctures on the disk. Say for each disk, you have only to take out at least 3 points. Then the proof is complete by a recent development. In other words, so you have a natural map, let's call it as Pn, sending G gamma into pure mapping class group, D2 minus punctures, sending V to psi V to the nth power, and actually this resulting to other theorem, Clay, Leininger, Langerhans, that such a map. So if you map a vertex to a sufficiently high power of pseudo-analysis of, such a map is quasi-isometric group embedding. So it is a simpler theorem which resorts to other standard theorem. Let's see. So yeah, that's it. Then you can embed writing Darting group into that pure mapping class group, which is also braid group. So let's see. And yeah, so this is the pure braid group with number of punctures is the number of strands. So let me briefly go over some of these consequences. So another intriguing question by far is that is the isomorphism problem, deciding whether two groups are isomorphic or not, solvable for FP subgroups, finitely present subgroups of mapping class group, say genus G. Okay. And Martin answered this by finding a certain pathological writing Darting group. So the isomorphism problem is not solvable for finite presented subgroups of certain writing Darting group. And by embedding that pathological writing Darting group into a mapping class group for sufficiently large genus for mod SG, where G is large enough such that the mapping class group contains that writing Darting group. And so our corollary is that the same is true for pure braid group, simply because you can embed this writing Darting group into certain braid group. Okay. So the remark is that it is far from, let's see, far from optimal. The number of strands that we find is far from optimal one. It can be very large, but still we can embed a writing Darting group into some pure braid group of large number of strands. And by embedding the pathological writing Darting group into pure braid group, you show that the isomorphism problem is not solvable. So remark. So when you're embedding writing Darting group into PBN, so our method gives, say, n is very large, like 2 to the 2 to the number of vertices to the square, but it is, I'm sure it is very far from optimal one. And the second application is yes. So it is not optimal. Yeah, it's not optimal. It's never optimal. In planar graph, it should be much easier. Yeah, much simpler, like linear on the number of vertices using crisp-fit approach. But our approach is, yeah, more complicated. Yeah. Let's see. So, yeah, application 2 is RAAGs in diff. Actually, yeah, it is a little bit of lie that I'm going to consider matrix on diffeomorphism group. I'm going to consider a subgroup of diffeomorphism group. So, and I'll just restrict myself to the study of sphere, two sphere, and consider area preserving diffeomorphism group of the sphere. So, area and orientation. Diffeomorphism on sphere. So smooth diffeomorphisms of the sphere. The reason why we restrict to area preserving is there's a right invariant metric. Actually, there are several metrics on symplectomorphism group of sphere, and some of them are, so many of them are just a mystery. For example, there's let me get to that later. So the metric that I'd like to talk about today is LP metric. So namely, if you have say a certain path from the identity, so it is isotopy to certain phi. Say you have phi t. Then you can talk about this LP length. So LP length is something that you try to define the length as natural as possible, then you get this one. So in other words, you consider the vector field by the time derivative and consider the p average, the p length of it. And then integrate over time. So this will be the LP length of an isotopy in symplectomorphism group. And then you have so this is the length, and length gives a length metric on the symplectomorphism group. So then we have a length metric. This is a dp on simp S2. So it is a chain rule exercise to show that this will be a right invariant metric. And that's where this area preserving condition is used. Then the theorem is that, I'll just say B, is that every Rayleigh darting group admits a QI group embedding into symplectomorphism group of sphere with LP metric where we restrict P larger than 2. So let me make some remarks regarding this. So there was a result by Misha Kapovich showing that so every Rayleigh darting group embeds group theoretically. There exists a group embedding into that symplectomorphism group of sphere. But in his construction, each vertex mapped to an infinite multiplication of double then twist. So metrically, that's a little bit harder to control. And let's see. So he's embedding. So Misha Kapovich asked the question whether it is a quasi-isometry embedding, but I do not know, and I don't think it is known. So each vertex maps to infinite multiplication of double then twist, and symplectomorphism group S2 is same as the Hamiltonian symplectomorphism group of sphere because there's no cohomology. Yeah.
The embedding of the theorem B is exactly what you have pointed out using the area.
You're right. So I'm using exactly the same embedding, but previously it was mapping class group, and now it is just the row diffeomorphism. So the proof of theorem B goes as follows. So idea B is as follows. So again, we consider gamma a tree. And as before, you have a map from writing the Artin group into the pure mapping class group of now sphere. Okay, instead of disk, you can do the same thing by embedding gamma in the sphere. And actually, it goes through the symplectomorphism group. You can go make it that each vertex maps to area preserving diffeomorphism. But not just that. Actually, we require a little bit more. So it is certain subgroup where Pn is Diffeos preserving punctures, neighborhoods, certain neighborhoods of punctures. So you can always do that. In other words, you just find the representative of mapping class in the symplectomorphism group of sphere. Okay. And we have only to show that Q. So we already know that we have a diagonal quasi-isometric group embedding. And this diagram commutes. So we have only to show that this map Q does not contract too much. Right? So what we consider is the universal cover. In other words, the homotopic classes of paths, which is 2 to 1, because it is a homotopy type is same as isometric group of S2, SO3. So, and we have lifting and Pn still 2 to 1. And this maps to the mapping classes. And you can lift it. So there is a natural lifting to pure braid group. And the map is whenever you have a homotopy class of paths in the symplectomorphism of a sphere, you just trace the disks, neighbors of the punctures, and see which braid it makes. That will be the image. And let's say Q and Q tilde, and one can show that Q does not contract too much. Okay, so coarsely, it is quasi-isometric. Okay, so yeah, I also should mention that there is a related result. So theorem A is also used in theorem by Denny and Robson in 14 with a similar flavor. So every writing Artin group embeds into, this time not Diffeo, but piecewise linear area preserving and orientation preserving diffeomorphism group of 2 disk. And I'd like to just conclude my talk by considering even one last dimension. So again, the motivation of this study was richness of subgroups of writing Artin groups and observation that usual construction of a given group, hyperbolic group into writing Artin group do not have much control on the target. It can be very, very complicated, high-dimensional writing Artin group. But still, theorem A tells us that we can embed into writing Artin group on a tree, relatively simple. In other words, can be indexed in a certain linear way. And even one last dimension, you can also prove that, so this is a joint work with Bldg, that every writing Artin group embeds into diffeomorphism group smooth diffeomorphism group of real line. Okay? And you can ask the same question for circle, but we do not know the answer. So let me stop here. Thank you very much.